Hello dear students. Let's continue with pumping lemma. We will learn one more example of pumping lemma. So here is example 3. We have to prove that this language given is not regular. Now try to understand the language first. Number of A's in the beginning must be equal to number of D at the end. So if there are 2 A's in the front, then there should be 2 D at the end. And number of B's must be equal to number of C. So if there are 3 B's, then there should be 3 C. So what can be the strings in this language? A, B, C, D. Just check. Number of A is equal to number of D. Number of B is equal to number of C. Oh, one more condition I forgot to write. M also should be greater than or equal to 1. Number N should be greater than or equal to 1. Number M also should be greater than or equal to 1. But even this string is allowed, isn't it? A, 2B, then 2C and 1D. Just check number of A's are equal to D, number of B's are equal to C. Even this string, triple A, then 1B, 1C and then triple D. Or this string, A, then 3 times B, but then there should be 3 times C and then D. All such strings are allowed. What do you finally say about this? 2A, 2B, 2C and 2D. Correct? This is also a string in the language because number of A is equal to number of D, number of B is equal to number of C. Just check. M can be equal to N. It's not given. So we can take, this is of the form A square, B square, C square, D square, isn't it? You can readily check here N is 2. N is 2 here. And M is also 2, which is fine because the condition is number of B and C must be equal and number of A and D should be equal. So as long as we preserve that condition, we have done well. Now this language is not regular has to be proved. So our usual steps, that let L be regular. Let L be regular. Then surely DFA exists. DFA exists with P states. Number of states are P. Let's consider some W. Let's consider a word W which is element of L, but length of W should be greater than P. What W will you consider here? You see, this can be one of the options that you can select: A raised to P, B raised to P, C raised to P, D raised to P. Tell me, aren't number of A's equal to number of D's and number of B equal to number of C? Yes. So this is element of L, and definitely, surely what we have is length of W is greater than P. Come on, length of this is 4 times P. And now we will decompose this string W into 3 parts, X, Y, Z. But remember, the condition was length of XY should be less than or equal to P. It can't be greater than P, and length of Y should be greater than 0. Now this W has P number of A's in front. Then it has B number of P's to follow, and then exactly the same number of C's to follow. And finally, at the end, we have P number of D's to follow. This is A raised to P, B raised to P, C raised to P, D raised to P. We want to split this string into X, Y, Z, but the first condition is length of XY should not exceed P. So how about taking these first P letters as XY? This is XY. And rest of these letters is Z. Rest of the letters are Z. But then the second condition says Y cannot be empty. So what you can do is you can take this letter, single letter A as Y. Okay. So now we have Y as single A and X as remaining A's, which is A raised to P minus 1. Just observe. So now what we have done is we have split this string into XYZ, W is XYZ, such that X is A raised to P minus 1, Y is single A, and Z is remaining, that is B raised to P, C raised to P, D raised to P, remaining string. Now let's construct a new string of the form X, Y square Z. We have taken I as 2. Remember the pumping lemma, the last step I am now doing, generating the new strings. So what will be the new string? X is a raised to p minus 1, correct? And y is single a, so we'll get a square due to y square, and rest z is this long sequence of p number of b's, p number of c, and p number of d. What is this new string? Look, how many a's have you got here? You got a raised to p plus 1, number of a's. Number of b's are still p, number of c are still p, and number of d are still p. Now, this is not the element of L, because number of a's are larger than number of d's. Check, number of a's must match number of d's. We have arrived at a contradiction. Hence, our assumption that L is regular is wrong and L is not regular. I hope you have understood. I hope. Now, I'll return to the same problem. Okay. And what did we say? W is a raised to p, b raised to p, c raised to p, and d raised to p. Not necessary. Not necessary. What about this? A raised to p, b raised to 2p, c raised to 2p, and d raised to p. Is this still the element of L? Yes, because number of b's are equal to number of c's. That's what the problem says. And number of a is equal to number of d. And note, length of w is very well greater than p, where p are the number of states of DFA. Now, can you decompose this into x, y, z? Now, you see this w that we are having is we are having p number of a's, and then we are having long list of b. This is 2 times p, and then we are having exactly 2 times p, 2 times p number of c's, and d's are exactly p. We have to decompose this into xyz such that length of xy should be less than or equal to p, and length of y should be greater than 0. How about taking these p characters as xy? This is xy. So length of xy is definitely up to p, it's not more than p. But what about y? What should be y here? Throughout these 3 examples, we have been taking y as a single letter. It's not a rule. It's not a rule. You can take last 2 a's over here as y. This is y, just for a change. So you check that this portion is y, and now x is remaining a's. So please try to understand, if w is decomposed as x, y, z, then x is a raised to p minus 2 and y is a square. Yes, length of y is still greater than 0, you watch. And z is that long sequence b raised to 2p, c raised to 2p, and d raised to p. This is xyz, which is perfectly legal, and we have followed all the rules. Now what if we construct w is x y square z, suppose. That is, we are pumping y 2 times. Then what will be the new string? What is x? X is a raised to p minus 2, correct? What is y square? Now y itself is a square, so you are going to get 4 a's, that is a raised to 4. And what about last term z? Z is that long sequence of b raised to 2p, c raised to 2p, and d raised to p. So what is this new string? This is a p plus 2. Just observe this. When collected, this will be a raised to p plus 2, and then followed by b raised to 2p, 2 raised to 2p, c raised to 2p, I'm sorry, and d raised to p, which is not the element of L. Please try to understand. We have got a raised to p plus 2 in the beginning. So we should have d raised to p plus 2 in the end, because number of a's must be equal to number of d's, but there is a mismatch over here, and this is not the element of L. We have arrived at a contradiction. So our assumption that the language is regular in the beginning and DFA exists is wrong. DFA does not exist. So I have made my attempt of explaining this in n number of ways. You can take some other string where surely the length of the string is greater than p, and it's not rule that you should take y as a single letter, because the condition is y should be, length of y should be greater than 0. You can take 2 letters, 3 letters, but see to it that length of xy together is at most p, it should not cross p. And then for some I, like here I we took as 2, for some I, if we are able to prove that the new string that we are getting is not the element of L, we have done with it. I hope you got this example 3 very well, and you also understood the statement of the pumping lemma, very well. Thank you very much.